Yes, good afternoon. Can I say that? Yes, good afternoon. It's really nice to see so many people in the audience from the industry, and we have quite a good mix of industry and academia. My name is Ananda, and I'm from Volvo Cars, coming from sunny Sweden, no, rainy Sweden. So, I will be presenting very briefly. I mean, we don't have a lot of time, of course, so we'll just very quickly skim through some of the work that me and my colleagues at the company have been forming on the DrivAer. A bit of a story before I start. Some of my colleagues were there in the AutoCFD4 in Barcelona, and they were feeling a bit left out because we were not really presenting something. So this time we made a concrete effort to actually make a contribution to this fora, and I hope it's fun and we learn something. Disclaimer: these are very qualitative, so in the sense you will see a lot of mistakes. But that's the, let's say, the inspiration for this kind of fora, where we try to learn from each other and make simulations better. Yes, so without further ado, we go into my agenda. Basically, we'll have some numerical details, and then I'll directly dive into the results, because we already know the DrivAer configuration. Burkhard explained it quite well in the beginning. As I said, some things to consider. We will be having more emphasis on qualitative trends. So we've not really dug into all the quantitative aspects. And something also to consider is I will be showing some of the measurement data from our wind tunnel, and they have been made under certain different conditions to what, let's say, the simulations have been performed at, but they're only here for illustrative purposes, just to understand how the trend could look in a real wind tunnel. Yeah. And we have to thank Ford for sharing the data for the wind tunnel. The numerical details, well, at Volvo we are running Star CCM, and this is one of our playgrounds. Since we use an earlier version, it's mainly because we do a lot of our development in the earlier versions. Hexahedral mesh, finite volume method, incompressible, all the usual stuff. The baseline model that we used was a DES, the K-epsilon elliptical blending. Something also to notice that we have a high vol plus, so that will be quite apparent when I show you some of our results. Our simulation loop typically consists of a steady state initialization followed by some unsteady flushing, and then we do our final simulation for around 1 second with a time step of around 2.5 e to the power minus 4 seconds, sorry. Directly diving into the mesh conversion. So here you actually look at the vol normal DS length scale, and you can, I mean, it's quite apparent that depending on the mesh that you have, your DS filter length is also going to change, and that's fairly visible here. And this mesh with 4 millimeters, this was quite problematic, and that actually ties quite nicely with what Charlie pointed out in his talk about the grid-induced separation, because this mesh did not behave as we thought it would, and you will see that in the results in the next slides. If we look at the mean velocity magnitude, again on a Y0 plane, and you can already see that there are some discrepancies between the different meshes. And that's, of course, to be expected because we have different filter lengths for the DES here. If I look at the mean CP and CD, and this is what I wanted to show again, and we see that the green line, which is the coarse mesh, does quite badly, and that could explain why we have, I mean, the green line is actually quite bad. The mesh resolution is insufficient. And we also see that the fine mesh is also kind of sticking out a bit there. And that can be slightly indicating that we are at the borderline of where we can, use mesh refinement for those cases. And we wanted to investigate a bit more into why exactly we saw the difference between the baseline and the fine mesh. And when we dug in, and now we do some very simple image processing. So we just take the two images that you see here. So here we have the velocity magnitude Y0, and then we just take a pixel to pixel difference. And then you can clearly see, okay, where exactly do we have the major differences? And I mean, we saw differences like throughout the car, more or less, the length of the car. So we see something in the plenum, in the underbody, of course, the C-pillar, and then at the base wake. So going down, making the mesh finer is seeming to kind of trigger different flow separation phenomena at different parts of the car. And this was something we are trying to understand and explain. We have not yet fully understood the full story, which is why we will use the baseline mesh for all the results presented in the remainder of my talk, mainly because it's based on the recommendations from the AutoCFD4 conference. So then we also did some very quick kind of scanning of the different turbulence models available in the solver of choice. We looked at IDDS K omega SST, we looked at DES K epsilon, IDDS LES whale, dynamics Magorinsky, Urans, and so on and so forth. And here I did a little bit of a thought experiment. What if you actually impose the 95% confidence interval from the simulations onto the experimental data? Now, this is actually not the case. The experimental data is definitely a lot more tighter, as Burkhardt explained. But I just wanted to just give a scenario where, okay, even if we had a really large spread in the experimental data, we see that at least our simulations are not even fitting in that. So which means that there seems to be quite a bit of variability in what we predict in the rear. And that can be due to a multitude of factors and type of mesh that we're using, type of models. Something to also consider here is to be consistent. We used exactly the same mesh for all of these models. So we did not change the mesh. So that can also explain partially why we see this kind of large variation between, you know, the different models, especially when predicting the separation in the rear. And of course, we see that the main deviation is mainly in the rear. And I think the CFD methods are fairly okay in the front. Of course, I need to probably fit them at probe 107 as Ford has done it. But I mean, it seems like until the C pillar, we are fairly okay. And here you can look at also the different CD values, and I kind of cluster them into two groups. I have the HR-LES cluster there. They seem to be fairly close by, all the LES and hybrid methods, the hybrid methods. And then you see that the LES is kind of slightly higher. Now, I would attribute this to having a poor mesh resolution for the LES. So we seem to kind of over-predict the separation there. And as you see, Urans is completely sticking out. So this is just a good way to kind of illustrate, you know, the large variability that you can have depending on what method you choose. If you also look at the mean resolved turbulent kinetic energy, so this is mainly an indication of, you know, what extent the domain is being solved using our LES. You can see that all of these two methods are what Volvo uses more often internally, the DES and IDDS. And if you see that all of the DES methods, they really do not predict, or they really do not solve any eddies in the upper half of the domain. So above the roof, you see that there's not much being created. Whereas in our LES simulations, we clearly see that we have quite a bit of separation that is kind of being predicted above the roof. And this is again an explanation of poor quality of our simulations, nothing else. And I did the same thing again, you know, so I took a pixel to pixel delta for the plots that I showed you in the previous slide, and this is fairly evident. All of the LES methods, you can see that we kind of trigger the upstream separation. We trigger separation quite upstream, and that can be a consequence of having poor wall resolution in these methods. We also did a tuning of our DES. That's something that, again, since it's one of our baseline methods, we try to play with the CDES factor, which kind of dictates when this RANST LES switching is happening. And then what is quite evident is if I use the default value as provided by Siemens, 0.2, we see that, okay, we have pretty let's say reasonable separation downstream of the C pillar across the bootlet, looks good. And we're again looking at a Y0 section here. And you can see that for a higher CDES, this thing suddenly vanishes. And now we don't have any separation being predicted on the bootlet. And that's also explained here in the pixel to pixel difference. And why this is mainly because by kind of increasing the CDES factor, we kind of trick the solver into believing that it's coarser than it actually is, right? So then you can kind of delay the separation point. This is also, at least in literature, been shown to be one of those tweaks to avoid grid-induced separation. So you can play with, CDES to kind of get the behavior that you think is more representative of your experimental data. The last slide, and this I think will be a bit of a controversial slide. This is mainly trying to compare all of our CFD simulations. So this is basically, I take the mean of all the simulations, and here we look at CP. And I tried to now do the right thing and put the confidence interval of the simulation spread on the simulations. And then we compare it with the wind tunnel data. And you can clearly see that it's the same thing. We are fairly good until the C pillar, and after that, all hell breaks loose, if I can say that. So there must be a lot of, let's say, internal investigation, both for us at Volvo and probably as a consortium here, to kind of understand, okay, what is the best practice here? How can we kind of reduce the gap and reduce the spread that we have in the simulation data? Because this seems to be the theme that we are seeing, not just in this edition of the conference, but past as well. So there must be at some point we make the change and shift and say, okay, now we're going to use this as the best practice. And that is the expectation that we have from this fora in the future. So in summary, well, the mesh convergence, I think that the AutoCFD4 based settings that we had, they were fairly good. They gave us the results that we thought were reasonable enough with our internal workflow. The turbulence model, well, I showed you that there was quite a large spread, and one needs to be really careful as to what one sets, how one sets up the simulations. And there's especially a large variation when we look at the downstream from the C pillar. And as I stated, our near wall resolution is insufficient for our LES simulations that we have showed here. The tuning coefficient was something interesting, and that's a good way to kind of trick people into believing that the separation can be pushed out of your simulation. So just play with CDES. And finally, for the wind tunnel data, as I said, there's still some work to do for us in the CFD community, and I think we are in the right track. With that, I would thank you all for listening to me, and I'm open for questions.